All right, three-dimensional trusses, trusses that just come like right out at you, like they're in the real world. See, so 2 weeks ago we worked on one-dimensional trusses. Last week we worked on two-dimensional trusses. This week we'll work on trusses in 3 dimensions. Of course, next week we'll work on trusses in 4 dimensions. No, just kidding. We'll move on to something else. But this week, trusses in 3 dimensions is going to seem very similar to what we did last week in 2 dimensions. So we'll go a little bit quicker since we're essentially going to be going over the same methodology we did last week. Again, we're just adding a 3rd dimension to it. We're again going to have, for each bar element in our truss, we'll have a local coordinate system, x hat, y hat, and z hat. We'll form a global coordinate system for our convenience to analyze the entire truss, x, y, and z. So our goal in this lecture is to develop the local stiffness matrix in the global coordinate system, just like we did last week on the 2-dimensional truss. So what we're looking for still is our local force vector, an equation for our local force vector given our local displacement vector in the global coordinate system, and we need to find what this K matrix looks like for 3 dimensions. We did that last week and we found what this matrix looked like for 2 dimensions. Now we need to find what it looks like in 3 dimensions. Now you'll note that since each bar element still will have a node at this end and a node at this end, there will be analyzing 2 nodes per bar element, but now each bar element can be displaced in an x displacement, a y displacement, and a z displacement. That means our our displacement vector will now have 6 elements. We can have forces applied at each node at each end in the x direction, the y direction, the z direction. So our force vector will have 6 elements in it, or 6 members in it. So the K matrix, which we're looking for, this is our goal in this lecture, is to derive the K matrix, or the local stiffness matrix in the global coordinate system, is now going to be a 6x6 matrix. And our goal in this lecture, in lecture 7, is to derive this matrix. All right? What we're going to do is fairly similar to what we did last week. We're going to follow the same steps. We'll first find the local stiffness matrix in the local coordinate system in the x hat, y hat, z hat direction. We will then find a transformation matrix and the inverse of a transformation matrix, which will relate the local coordinate system, the x hat, y hat, and z hat coordinate system, to the global coordinate system, x, y, and z. In 2 dimensions, the relationship between the local coordinate system and the global coordinate system could be defined simply by 1 angle. What we're going to find here is that we're going to need 3 angles to define the relationship between the 2 coordinate systems. We're going to have an angle which goes from the x hat axis on the bar to the x axis, the global coordinate system. We'll call that theta sub x. We'll also have an angle that goes from the bar to the y axis. We'll call that theta sub y. And we'll have an angle that goes from the bar to the global z axis. We'll call that theta z. Once we have the transformation matrix to go from the local coordinate system to the global coordinate system and its inverse, we can apply the same linear algebra trick we used in 2 dimensions to derive the local stiffness matrix in the global coordinate system. And of course, once we have this matrix and we can analyze and find out what the specific local stiffness matrix is for each bar element in our larger truss, we can go ahead and assemble the global stiffness matrix as the additive sum of all the local stiffness matrices, again, just like we did for the 2-dimensional case and the 1-dimensional case. All right, so let's go ahead and get started. Let's move on to the next video.